this second worksheet for chapter 10, we're gonna explore the gas laws. You will have to read the problem carefully and extract the information and analyze what information are given in order to correctly set up the problem. Problem 1. A gas with an initial pressure of 780 torr, so that's going to be your P1, and a volume of 150 liter, that's going to be your V1, P being the symbol for pressure and V being the symbol for the volume, and we are in the initial state. We apply a change. So what change is applied? It's compressed to a volume of 32 liter. Therefore, this is the final volume. This is our new volume after the stress is applied to the system. It's going to be our V2. And now we're looking for the pressure of the compressed gas. So we're looking for P2. Because we have here a stress that has been applied, which means we have a change happening. When there's a change, we always use the same equation. P1 V1 over N1 T1 equal P2 V2 over N2 T2. Okay? Every time you see that there's a change in volume, a change in pressure, a change in number of mole, a change in temperature, you'll be using this equation, this general equation. So let's take a look. P1 V1 over N1 T1 equal P2 V2 over N2 T2. We are given no information whatsoever on the number of mole or the temperature of the system. Therefore, we assume that N and T are constant. We are therefore left with P1 V1 equal P2 V2. We have a P1 and a V1, and we have a V2. Therefore, we'll be looking for P2. To isolate P2, we're going to divide on each side by V2. So the V2 cancel on the right side, and we get a new equation that is P2 equal P1 V1 over V2. Now that you have our equation, we're going to plug in the data. P2 equal initial pressure 780 torr time initial volume 150 liters over the compressed volume 32 liter. Check that your unit cancel properly. You're left here with a unit for pressure. When you plug this into your calculator, you get an answer of 3.65625 times 10 to the third torr. Sig figs wise, 2 sig figs here. Remember that the trailing zero here doesn't count because there's no decimal. 2 sig fig here, 2 sig fig here. So your answer is given to 2 sig figs as being dropping a 5, rounding up, 3.7 times 10 to the third torr. Next problem. Again, we're going to identify a balloon with a volume of 4,320 cubic centimeter. This balloon is at a temperature of 25 degrees Celsius. Remember, in this chapter, all the temperature have to be converted to Kelvin by adding 273.15. So this is our initial volume. So we have our V1 here, and this is going to be our initial temperature, T1. I'm going to immediately add 273.15 to get my initial temperature being to 1 decimal place, 298.2 Kelvin. Okay. When I add these, I get 298.15 Kelvin, but it's an addition. 1 decimal place, 2 decimal place, so my answer should be given to only 1 decimal place. Therefore, T1 is equal to 298.2 Kelvin. Here is the stress. We're heating the system to the new temperature, therefore it's going to be our T2. And our T2 will be 95.0 Celsius. Adding immediately again, remember no Celsius, only Kelvin, add to 73.15, 368.15 Kelvin, but again, same thing. 1 decimal, 2 decimal, answer to 1 decimal, so my T2 will be 368.2 Kelvin. And what will we be looking for? What is the new volume? So we're looking for V2. Again, here is our stress, our change. Therefore, we're going to be using the equation, the general equation, P1 V1 over N1 T1 equal P2 V2 over N2 T2. Let's check. No information on the number of mole and no information on the pressure. Therefore, P and N are constant, and here is our new equation, V1 over T1 equal V2 over T2. We are given V1 and T1. We are given T2. We are looking for V2. Therefore, I need to isolate V2. So I'm going to time by T2 on both sides. When I do this, my T2 cancel, and I get a new equation where V2 equal T2 time V1 over T1. Plug in the data. T2 in Kelvin is equal to 368.2 Kelvin. V1 is equal to 4,320 cubic centimeter over T1 to 98.2 Kelvin. Check that your unit cancel. Oops, wrong one. Check that your Kelvin cancel. You're left with the unit for volume, which is cubic centimeter. Plug this into your calculator. 5,334 cubic centimeter is the answer from your calculator. Sig figs 4, 3, 4. Again, remember 4,320. It's only 3 sig figs because the 0 right there do not count. Your answer needs to be given to 3 sig figs as either 5,330 cubic centimeter or 5.33 times 10 to the third cubic centimeter. Next problem. Okay, so a little bit more data, but it's okay. We can just take our time and analyze. A gas inside a piston occupies a volume of 220.0 cubic centimeter at a pressure of 1.03 bar and a temperature of 100 Celsius. Therefore, all of these are connected. That's my V1, my volume, cubic centimeter as a unit, my pressure in bar, P1, and my temperature here, T1. Do not forget to add your 273.15 to 1 decimal place. 373.2 Kelvin is my T1. a change, a stress is applied because this gas is cold to room temp. Therefore, here is my new temperature. That's going to be my T2 plus 273.15 to 1 decimal place to 98.2 Kelvin is my final temperature. The volume drops to, so that's my new volume here, my V2. And I'm looking for what is the pressure. So I'm looking for P2. Again, here's my stress applied to the system, my change. Therefore, I'm going to be using the general equation P1 V1 over N1 T1 equal P2 V2 over N2 T2. We're given no information whatsoever on the amount of gas, the number of mole, therefore N is constant, and we have a new equation as being P1 V1 over T1 equal P2 V2 over T2. We're given a P1, a V1, and a T1. Don't forget Kelvin. We're given a V2. We're given a T2. Don't forget Kelvin. We're looking for P2. How are we going to isolate P2? We need to time by T2 on both sides. Therefore, T2 cancels. And then we have to divide by V2 on both sides. So V2 cancel, and we end up with the new equation that is P2 equal T2 P1 V1 over T1 times V2. Plug in the data. P2 equal T2 298.2 Kelvin. P1 220.0 cubic centimeter. Oh no, sorry, that's V1, and I was looking for P1 1.03 bars. V1 220.0 cubic centimeter divided by V2 118.0 cubic centimeter time T1 373.2 Kelvin. Check that your unit cancel properly, the cubic centimeter with the cubic centimeter, Kelvin with the Kelvin, and I'm left with a unit of pressure, which are the bar. So when you do this on your calculator, don't forget that you have to divide, and these two have to be below the division line. Plug this into your calculator and you get 1.5344 18769 bar, sig figs wise 4 3 4 4 4. So my answer needs to be given to the least amount of sig fig, 3 sig figs. Dropping a 4, my answer to 3 sig figs is 1.53 bars. Next question. Here you're given some very important information. You're told that you are at STP. STP means standard temperature and pressure. You have to know those. The standard temperature is 0 Celsius or 273.15 Kelvin, and the standard pressure is 1 atm or 760 millimeter of mercury or 760 torr. Okay, In general, we'll use Kelvin and ATM. So the question is asking, how many moles of a gas occupy a tank with a volume of 1.2 cubic meter? So you're only given a volume. There's no stress, no change, okay? Very important. You don't see. We're looking for how many moles of gas, and we're given a volume, we're given a relationship, because there's no stress applied. We're going to be using the ideal gas law, PV equal nRT, where, since we are STP, this is our temp and this is our pressure. So we are given here a temperature and here a pressure. Very important to remember, R is a gas constant. Therefore, R is a set value of 0.08206 liter ATM mole Kelvin. For that reason, you have specific unit for the volume, it has to be in liter. Specific unit for the pressure, it has to be in ATM. Specific unit for the temperature, it has to be in Kelvin, and your number of mole will end up being given in the mole unit. We're looking here for the number of mole, and we're given the volume. Therefore, we have to solve for n. In order to solve for n, so I'm going back, I have PV equal nRT, right? I need to isolate n. So what I'm going to do is I'm going to divide on each side by r. So r cancels, and I'm going to divide on each side by t. So t cancels. And I get a new equation as being n, the number of mole, equal PV over RT, where I'm going to now plug in the data. Let's just put this right here. The pressure is the standard pressure, 1 atm. The volume is given to me, but here, notice that the volume is in cubic meter, so I have to do the conversion, 1.2 cubic meter time, cancel your cubic meter, convert to liters. This is equal to 1,200 liters, because units have to be liter in order to use the R, the gas law constant, 0.08206 liter, don't forget your unit, ATM mole Kelvin, time T in Kelvin to 73.15. Plug in this your calculator, check that your unit cancel properly, ATM with ATM, liter with liter, Kelvin, Kelvin with Kelvin, so you're left with mole, which is the unit you're looking for. This is equal on your calculator to 2 sig figs to 54 moles. Okay, why 2 sig figs? Because the one here is exact. This is 4 sig figs, this is 2 sig fig, and this is exact, okay? For your STP, those values here are exact. Therefore, my answer is given to 2 sig figs. Here, I'm sorry, last problem, problem 5. What is the pressure? Okay, so what is the pressure? So we're looking for P of a 12.5 mole of gas. So we're given N at a temperature of 360 K and a volume of 5.2 liter. temperature of 360 K, volume of 5.02 liter. All of them are connected. Again, there's no stress, no change. Therefore, we're going to use the ideal gas law. That requires us to use specific unit due to the presence of the gas constant R. We're looking for P. So I'm going to isolate P and divide by V on both sides. So my V cancel. And I get that P is equal to N, the gas constant R, the temperature of the gas T over the volume of the gas. N is 12.5 mole. R is the gas constant, 0.08206 unit liter atm mole Kelvin. The temperature T, 360.0 Kelvin. Everything divided by the volume in liter, 5.02 liter. Check that your unit cancel properly, the mole with the mole, the liter with the liter, the Kelvin with the Kelvin, so you're left with a unit of pressure. You plug this into your calculator and you get 73.5597 atm, since it's the unit, the pressure that is left here. Sig figs wise, 3, 4, 3, 2, since there's 0, oh sorry, 360.0, so 4, 3, 4, 3, 2, 3 sig figs. My answer is, dropping a 5, rounding up, P is 73.6 atm. In problem number 6, you have here a 10-liter gas cylinder at a temperature of 298 that contains an unknown gas. So let's just like draw a picture. I have here a gas cylinder with an unknown gas. This cylinder has a volume of 10.0 liter and a temperature of 298 Kelvin. Okay, and it contains an unknown gas. Let's just do unknown gas particle. Okay, with a valve at the top. It looks like a cross, but it's a valve. So what happened is 48.0 grams of this gas are released from the cylinder, and this consists, and therefore this when the 48.0 grams of gas are released, we have a pressure loss of 3.67 atmosphere, okay, which means that these 48 grams represent that pressure. If you recall the law of mass, Dalton's law, we mean that in this container we have a total pressure, and the total pressure is actually equal to the pressure of the gas left in the tank plus the pressure of the gas that has been released. Okay, and actually this both pressure, the total pressure, the pressure of the gas that is left in the tank, and the pressure of the gas that has been released from the tank, okay, from the cylinder, then they both have the same volume and the same temperature. So first question is asking about what? So we have the volume, the temp, we have the mass for the unknown gas, and we know the pressure of this unknown gas, okay? And here the problem asks for how many moles of the gas were released from the tank. So we have here, one volume, one pressure, one temperature. So we're going to use PV equal nRT. And we're going to solve for n. To solve for n, we're going to divide on both sides by RT. Therefore, we have the R cancel, the T cancel, and we get n equal PV over RT. Plug in the numbers. The pressure is 3.67 atmosphere, the volume 10.0 liter over 0.08206 liter ATM mole. Kelvin for the gas constant, and the temperature 298 Kelvin. Check that all the units cancel properly. Pressure with pressure, liter with liter, temp with temp, Kelvin with Kelvin. So we have left moles, and three sig figs, sorry, we get 1.50 mole of this unknown gas. Okay. Sig figs wise, 3, 3, 4, 3, answer to 3 sig figs. If we look at the next question, we're looking for the formula mass, the molar mass of the gas, okay, in gram per mole. We have grams here, and we have grams of gas here, and we have mole of gas here. Therefore, so that was for, if I just go back here, answer for A, and if we do B, the molar mass, which is the same as the formula mass for the gas, will be equal to the gram of gas, 48.0 grams, over the mole of gas. This represents 1.50 mole. Okay, so we have the unit we were looking for, grams per mole, and 3 sig figs, 32.0 gram per mole. So now we can easily answer question C. Identify the gas as one of the following. Well, let me pull this down and take a look. What's the molar mass of helium? Look at your periodic table, 4.00 gram per mole. Neon, 20.18 gram per mole. Argon, 35.95. So as of now, none of them will match. Now be very careful with these two here, because nitrogen is N2, so it's 2 times 14.01, 28.02 gram per mole. Oxygen O2, 2 times 16.00, 32.00 gram per mole. And then for the sake of it, carbon dioxide, 1201 plus 2 times 16, 44.01 gram per mole. Recall that this is carbon dioxide. Okay, so we have a match. Here's our match. Therefore, what is this unknown gas? Match the molar mass of oxygen gas, O2, 32.00 gram per mole. So our unknown gas is oxygen that is contained in this container, in this tank. Next question. A cylinder of gas contains 100.0 mole of nitrogen gas and 25 mole of oxygen gas. The overall pressure, so we're given here, the total overall is the same as the total pressure, so we have a P total that is equal to 214.2 psi. We want to find the partial pressure of N2 and of O2. So first of all, what is the partial pressure? The partial pressure of the gas X is equal to the number of mole of gas X over the total number of mole of gas and time by the total pressure. Okay, this that you have right there, it's actually called the mole fraction. C. Therefore, the partial pressure of gas X is equal to the mole fraction X times the total pressure. We're given the total pressure here, so we need to find the mole fraction. In order to find the mole fraction, we need to find the total number of mole in the container, okay? So let's draw a picture again. Here is my container. Contains two different gas, nitrogen and oxygen. Okay? This container has a total pressure of 214.2 psi. This container contains N2 gas, and the number of mole for N2 is 100.0 mole. This container contains as well O2 gas, and the number of mole of O2 is 25.0 mole. We have therefore a total number of mole being 125.0 mole. Okay, since you can add the moles, it's just like it's a countable unit. We can easily find the P partial pressure of N2, which is going to be the number of mole of N2, 100.0 mole, over the total number of mole, 125.0 mole. Everything by the partial pressure, 214.2 psi. The partial pressure for O2, similarly, following the formula, will be the number of mole of O2, 25, over the total number of mole in the container, 125, times the partial pressure. Plug this into your calculator. The first one to 4 sig figs will actually be 171.4 psi. Why 4 sig figs? 4, 4, 4, answer to 4 sig figs. For the partial pressure of O2, we get 3 sig figs, and the calculator gives you 42.8 psi. We can always check that the sum of the partial pressure is equal to the total pressure. 171.4 plus 42.8 equal 214.2 psi, which is the total pressure. Because you need to remember Dalton's law, the sum of the partial pressure of a mixture in the container is equal to the total pressure, okay? It's called Dalton's law. Finally here, last problem 8 talks about diffusion and effusion. Just remember that mnemonic way, effusion starts with E escaping the container, the gas escape, okay? You have a balloon that is filled with neon, molar mass of neon, check your periodic table, 20.18 gram per mole, and another balloon is filled with argon, molar mass of argon per your periodic table, 39.95 gram per mole. The question is, which of this balloon will deflate the fastest? And don't forget that you are asked to explain. Well, the lighter is the gas, the faster the gas will actually escape. Therefore, the fastest the balloon will deflate. Neon is the lighter gas, therefore will deflate the fastest. Argon is actually heavier, therefore this one will deflate the slowest.